Okay, in this problem, we're asked to calculate the amount of energy that's stored in the magnetic field of a solenoid. There's a couple of different ways we can approach this problem. We could calculate the magnetic field everywhere and then use the fact that the magnetic field density is equal to B squared over 2 mu naught. Instead, though, in this problem, we're going to use the fact that the energy stored in a magnetic field for an inductor is 1/2 times L times the current running through the inductor squared. So the real challenge then becomes to calculate what the self-inductance of the solenoid is. We're going to follow a standard approximation with solenoids, namely that the magnetic field is uniform throughout the interior of the solenoid and it's zero outside the solenoid. This, of course, isn't quite true at the edges, but we're going to make the approximation in order to simplify the problem and come up with an estimate of the answer. The inductance, self-inductance, is equal to the number of turns multiplied times the flux through one turn over the current running through the solenoid, or in this case, any sort of conductor. So for this particular problem, the inductance L is equal to the number of turns times the magnetic field flux. Well, the magnetic field is equal to mu naught times the number of turns per unit length, which I'll write this way, times the current. So there's a value of the flux, or excuse me, the B field. In order to get a flux, we have to multiply that times the area of the solenoid and divide the whole thing by the current. So we can write down the inductance is N squared over L mu naught times pi times R squared. Let's go ahead and put this together. The number of turns is given as 574 squared, no units, just the number of turns, times a constant mu naught, 4 pi times 10 to the minus 7 newtons second squared per coulomb squared, times pi times the radius of the solenoid, which is given as 0.02 meters, 2 centimeters. And we have to square that to get the area. And then we have to divide the whole thing by the length of the solenoid, which is given as 32 centimeters, or 0.32 meters. Combining this all together, we can calculate the inductance. We find that the inductance is equal to 0.00163 henries. In order to calculate the energy stored then, we just take 1/2 times 0.00163 joules per amp squared is a henry, times 10 amps squared, the current carried, squared. And by doing this, we find that the total energy stored is 81.3 millijoules.